All right, here we are once again for part 2. We're just going to work through a few examples and we'll be on with our lives. So this example here, okay, simmer down a bit. Okay, so you know what? This example here in the beer vector mechanics book, it looks like this is meant to be a tabular problem where you, sorry, not a tabular, but a, well, maybe you should say that. It looks like one where you could just look up the formula in a table, and you could, but I decided that I'll have a little fun, and so I'm going to solve this using an integral, just for fun. Okay, I believe so. Yeah, that shouldn't be. It's a parabola. It's just an ordinary parabola, although basically I'm going to solve for the equation of the parabola. I'm going to solve for the equation of a parabola. Let's see. So we have this. So let's see. So we're going to have something like the vertex is at 15, right? The vertex is at 15, oh no, 0, comma 15. So first thing I want to do is I want to get the equation for the parabola. And this is how you would actually find the centroid of an unknown shape. If you don't know the shape exactly, you're going to actually have to derive the formula for the shape first. So let's see. I can do the following. Well, I know that parabola is of the general form y equals ax squared plus bx plus c, right? And then let's see what else. I know c in this case is going to equal 15 because here this is clearly like so. The vertex is clearly at 15 when x is 0. Then let's say, what else could we do? Well, huh? Let's see. Well, we have 2 points that we know. We have, let's say, what if I use the points 0, comma 15, and 80, comma 50. Oh, sorry, 80, comma 65. So again, the reason I'm doing this is because before I can take the integral, I need the equation. 80, comma 65. Or, let's see, is this integral going to be too difficult to do? Yeah, I don't know if I want to do this. Maybe I'll just use the, I'll use, when I demonstrate the integration, I'll use a little bit different method, different problem. I'll show the tabular method for this one. Never mind. Simple enough. Okay. So if we go again to that formula, that table with the formulas, this is a parabolic spandrel. And the formula for a parabolic spandrel, if you look here, this is called a parabolic spandrel. A spandrel is a slight piece like this. Below it's a rectangle here, above it's a spandrel. So we're going to have 2 pieces, a 80 by 15 rectangle, and then a parabolic spandrel here, like this, with a dimension here of 80 and this of 50. And so I'm going to call this one piece 1 and 2. So if you look in the book, what it shows is, if you look in the formula, for the rectangle is going to be easy. It's just going to be in the middle of the rectangle. The spandrel, on the other hand, is going to have has a formula like this. It labels it as, it gives us the dimensions A and H, A and H, and it states that the coordinates are at the x bar and y bar, that the x bar measured from this point the origin here, it says that the x bar is located at 3a over 4, 3a over 4, and the y bar, the y centroid, the vertical centroid of that piece, is going to be at 3h over 10. And it also says that the area is located at AH over 3. AH over 3. This is A, this is H, like so. Okay, so for this piece, the x bar is going to be at 3 times 80 over 4, which will be, okay, 3 times 80, actually this is comes together to be 20, so that has to be at 60 millimeters. And the y bar, let me write it a bit further to the left. The y bar is 3h over 10, so 3 times 15, sorry, 3 times 50 over 10.
Would there be a way to just calculate the total area and subtract that circle? Or the part of that circle?
Not really. It's going to be just as complicated.
Oh, okay.
Oh, why did I keep writing 15 in there? 3 times 50. 3 times 50 over 2. Over, sorry, 10. However, what is wrong with this? See, I need to add the fifth. This formula is defined. You always need to be very cognizant when you're. This is the danger of using formulas. This is the danger of using formulas. You always need to be very cognizant of where the origin is. See, in this problem, or in this formula that the book gives us, the origin is conveniently located at the bottom left of the spandrel. But here the origin is 15 units below this. So we're actually going to need to add the additional 15 to get up to here. So this is then 30. 30 millimeters.
If something started over to the right, then could you then add something to the x bar? Okay.
And then the area is going to be AH over 3. So A is 80, H is 50 over 3, which comes to 4. Oh, that's just ugly. AH over 3. I'm just going to let it be an ugly decimal. 80 times 50 over 3, 1333.3. Okay, and then for the rectangle here, obviously the x bar is just 40 millimeters. The y bar is just 7.5 millimeters. 7.5 millimeters, and that's it. 7.5 millimeters, and the area is 15 times 80, which is 1200. 1200 millimeters squared. Millimeters squared. And then I can simply say for the entire thing, combine. I could use a table or I could just write it out. In this case, it's so simple. X bar is going to be 60 times 1333 plus 40 times 1200 over 1333 plus 1200. And this comes to 16 times 1333 plus 40 times 1200 all over the summation of 1333 plus 1200. And I get 50.53 inches, or sorry, millimeters. millimeters. Then the y bar, again, to combine these together, is going to be, let's say, 30, yes, times 1333 plus 7.5 over 1200 over 1333 plus 1200, oh, not 12,000, 1200, and this comes to 13 times 1333 plus 333 plus 7.5 times 1200 over 1333.333 plus 1200, and I get 3.675 millimeters. Wait, something's not right there. Something's very wrong there. Something's not right. Oh, I entered 12,000, not 1200. That's why. 19.34. I feel happy now. 19.34 millimeters. And that will be the X bar and Y bar for this shape here. Okay. Let's see. Oh, let me show you how to do something integration. Let me show you integration for something a little bit simpler first. So we have learned, I've told you, and we can see in the formula here, or in the table here, that the centroid for a triangle is 1/3 from its base. What if I want to prove that formula? So derive the formula for the centroid of a triangle. Centroid of triangle. I will do this in terms, I'll try to do this generically in terms of variables instead of specific values. I want to actually prove this. Okay. So let us say I have the following equation. All right, let's say I have a triangle with base A and height B. So for simplicity, I'm going to position the triangle as a right triangle with its right angle at the origin, because that will make things a lot simpler. So here's the triangle, and I'm trying to derive the formula for its centroid. Actually, you know, instead of A and H, I'll use B and H for base and height. That's more familiar to people. Say B and H. Okay. Well, the first thing I'm going to need to do is I am going to need to derive a formula for this triangle. And this formula is going to be simply y equals h minus h over bx. It's simply a linear equation. Oh, that shouldn't have a y bar. That should just be y. The equation for this line here, in terms of the h and the b, is h minus h over bx. Because this is the slope, rise over run, h over b. The intercept is h, so the equation for that must be h over bx, or h minus h over bx. Okay, so the first thing I'm going to do is find the x bar. The equation's already set up for this. Let's do this. Find x bar. Now, consider this. So we're going to have something like this. The equation. And I can check that this equation is accurate, because if I put in 0 for x, I get h. And if I put in b for x, I get 0, which is exactly what I would expect. Y equals h minus h over bx. But in order to perform an integration, I need a differential element. And so I'm going to use a little dA. My dA is going to be like this, dA. And my dA, if I extract this out, make it a little bigger, the width is going to be dx, and the height will simply be h minus h over bx. So here we will say qy, the first moment of area off of the y-axis, if you remembered, was the integral of x dA. However, dA is simply length times width is h minus h over bx times dx. So that is going to be the integral of h minus h over bx times x dx. And so then this will be the integral of h squared minus h over bx dx evaluated from 0 to b. Yes?
Where'd you get the other x?
Ah, this is from, where did I get this other x?
Oh, xdA.
xdA, yes. Okay. So this is calculus in terms of constants. So then the integral here is going to be, if I evaluate that, that is going to be h cubed over 3 minus h x squared over 2b evaluated from 0 to b. Oh, I cannot write. That's h. Sorry. Oh, that's just h. Did I really screw that up? Man, I screwed up an integral. I can't believe that. I screwed up the easiest integral you could possibly have. I am sorry. Derp, herpa derp. That's just h squared x. Sorry. H squared x here and hx squared over 2b. Evaluated from 0 to b. And the 0 will come out to be 0, so we should get h squared b minus, let's see, this is bothering me a little bit. Something's not right here.
Didn't you distribute the x as you take the parentheses out?
Oh, you're right. Sorry, I did screw up something here. That's what was getting me. hx squared. That's what's getting me. Sorry. Helps if you transcribe things correctly. Derp. Okay, that makes me feel better. Yeah, we need to distribute the x first. So it's actually just h, isn't it? hx minus hx squared b dx. That makes me feel better now. Okay, and so now this is hx squared over 2 minus h x to the third over 3b, right? Evaluated from 0 to b, and let's see. So yeah, this is turning out the way I like it then. This is going to be then hb squared over 2 minus hb to the third over 3b. That becomes squared, that goes away. So we end up with, okay, let's combine these together. This is 3 over 6 hb squared minus 2 over 6 hb squared. And finally, this will just be hb squared over 6. So that's the qy. And then the a Okay, that's simply the integral. We know you know to find the integral, the area under a curve, the integral of dA, or the integral of h minus h over bx dx evaluated from 0 to b, and that's going to be hx minus h over b x squared, or h over 2b x squared evaluated from 0 to b, and that is going to be hb minus hb minus hb squared over 2b, or that goes like that, right? So that becomes just a b instead of a b squared. So I get hb minus hb over 2, or the area is simply equal to hb over 2. Questions so far? Okay. Oh, you got this? Okay.
No,
Oh,
I don't.
okay. We'll give you a minute. It's not. Why didn't you got it? It's not like we went in circles a little bit there or anything. I know what you're talking about. It was always right from the first time. You saw nothing. Pay no attention to the man behind the curtain. Yes.
So in practice, will it ever make sense to do your dA horizontally and do x as a function of y?
We will need to do that for the second one. We'll need to use a horizontal element of integration for the second one.
And also, will we ever need to use polar integration for this?
Not for this class, but in some cases, yes.
Okay, good.
I try to keep the integrals you have to do on the exams fairly simple. Okay. I'm trying to test your knowledge of statics, not necessarily knowledge of calculus, but you do need to know some calculus to do this. And then I think I could probably just finish this one out here. Nah, no, I won't. I'll put it on the next one, I guess. Okay. So we know, I'm just going to summarize a bit, Qy equals HB squared over 6. And I know that A is HB over 2. So I'm just transposing stuff from the other slide. And our general equation, again, is y equals h minus h over bx. Okay. But our x bar, then, is qy over a, this is where it comes together, is hb squared over 6 divided by hb over 2, which is then equal to, I learned in elementary algebra class that to divide by a fraction, you multiply by the reciprocal. So I'm going to do that. 2 over hb, boom, 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 and I get b over 3 for x bar, which is exactly what we expect. The x bar is 1/3 of the base. And if we do this right, we should get the same thing for the y bar. So I'm going to try to fit this on one slide. Try to save some room here.
Question.
Yes.
That only applies if the triangle is like in that direction.
Yeah, that only applies if the triangle's in that direction. You'll have to derive it for other setups in other scenarios. Or more likely, you'll divide it into subtriangles and things like that. Like if you have for example, if the question was, this only works if the triangle is orientated like that, and I said yes. But what you could do is, for example, if you had a triangle like this, that one side is longer than the other, you could set up an integral to solve for that. Or you could just realize, oh, this is two right triangles positioned right back to back, and then just combine them through formula, through a table. Okay, so in order to get the y bar, I'm going to need to do an area integral with a horizontal element of integration. So in order to do that, I'm going to need to rewrite my equation. It was like this. We do have this, and so first we need to solve this for x. So we get x or h minus x or h minus y. H minus y equals h over bx, and then x equals b over h times h minus y, or simply b minus b over hy. Yeah, that sounds about right. So this is x equals b minus b over hy. And now our element of integration is going to be horizontal, like this. And our element of integration, instead of having a dx, it's going to have a dy. And the width of this is going to be b minus b over hy, like so. Then, let's see. I will simply say the first moment of area off of the x-axis, the qx, is going to be the integral of y dA. And again, dA here will be b minus b over hy dy equals, so we'll have the integral, let me write this out, the integral from 0 to h, this is at 0, this is at h, 0 to h of y times b minus b over hy dy equals by minus b over hy squared, b over hy squared, the integral from 0 to h, and this is then by squared over 2 minus b over h, or 3h, y to the third, evaluated from 0 to h, which is then b h squared over 2 minus b h to the third over 3h, boom, boom, that's squared, and this will all come, qx then, will come to, let's see, this is just 3bh squared over 6 minus 2bh squared over 6. So very similar to the qy, qx will equal, will simply equal bh squared over 6. So that's the first moment of area for off of the x-axis. And then y bar will equal qx over a. It's the same area, bh squared over 6 over hb over 2, or, oh, that does not look right. So this is bh squared over 6 divided by hb over 2, which equals bh squared over 6 times 2 over bh, boom, 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 and I get finally h over 3 for the y bar. So in other words, after all of this, we see that the centroid is indeed equal to b B over 3, comma, H over 3. Exactly what we expect. So these formulas can be derived. These formulas can indeed be derived. Thoughts? Huh? Too much?
Yeah, for one process.
Just one problem.
Or just a triangle.
Just a triangle. That's for the triangle. Or if we want to do a really trivial problem, we could put a square centered at the origin and prove that its centroid is at the origin.
There we go.
We could go through all this proof just to prove something incredibly trivial.
Engineers don't waste their time on that.
It's tempting. All right, questions on this. So what did I do? Yes.
So just B over 3 and not B over 2?
The final answer?
Oh, yeah.
Yeah, it's for both of them. The centroid is 1/3 from the edge. Okay. Yes. So no, it would not be B over 2 or H over 2. It would be B over 3. Yes. Question?
Are you gonna show it, like on the test, it's gonna say use integration to solve for this?
Yes.
Okay.
Okay.
Just making sure.
All right. Let's see. Can we solve for this one? What could we do? This one looks slightly evil. Well, let me think. Yeah, well, I can see that the Y bar or the X bar is going to be fairly easy to do, right? It's the Y bar that's going to be tricky, right? Well, let's give it a try. As a famous instructor once said, take chances, make mistakes, and get messy. Anyway. Okay. So, here. Let's see. I'm going to use for the Q. Let me just, I don't know I don't know what I'm doing. Let's see. So again, we want to find the centroid of this via direct integration here. Now, let's do the the X bar first. That's going to be the easy one. And let's see. This is going to be our dA. For X bar, this will be our dA. And this dA is going to have a width of dx and a height of 2b minus cx squared minus kx squared. However, they want us to find this in terms of a and b. So maybe I don't necessarily want to do that. See, here's the thing. They want this in terms of a and b. So maybe I don't necessarily want that. That's going to give me trouble, I think, to have that many constants. I would perhaps like to get this in terms of a and b at the start. Get these equations in terms of a and b. So let's see. How about this y equals kx squared? How about this one is already in terms of a and b, so that's not going to, well, no, it's not. The c isn't. So I know that this thing has a coordinate of a comma b, right? That's one of its coordinates. So therefore, that I can say b equals, oh my goodness, let me just, b equals ka squared, so k therefore is equal to b over a squared. So this equation then is y equals b over a squared x squared. I'd like to get rid of the c and the k to start out with. Because again, they're asking for this in terms of a and b. They want to find the direct integration of the centroid of the area shown in terms of a and b. So if possible, I'd really like to get rid of that. Thing here. Oh, we're in luck. I was thinking the y bar would be rather difficult. It's not. Why? Actually, no, never mind. I'm lying. I'm lying. Never mind. I'm lying. I'm sorry. Well, maybe not. Let me think. We'll see. Huh? It looks symmetric. I'm not sure if it's symmetric though. Let's solve for this here. It kind of looks symmetric, but I'm not quite sure. It kind of looks symmetric about this line here, but I'm not quite sure. But I still need to get c. So let's get y equals 2b minus cx squared. And I have the known point again, a comma. Actually, you know what? No, that's not going to work. The known point a comma b. So b equals 2b minus c a squared. So that will be negative 2b, or sorry, negative b. Negative b equals negative ca squared. B equals ca squared, and c equals b over a squared. So this equation now is y equals 2b minus b over a squared. 2b minus b over a squared, yeah. X squared. Y equals 2b minus b over a squared x squared. To me, this shows that this is a symmetric parabola, isn't it? This is we have a symmetric system now. We have a symmetric system. Definitely. Huh?
Sorry, does that mean that we just need X bar?
Exactly. We only need X bar because I can see by the slope here that that via the equation for the only thing that's changing with respect to X is this term here. So I can clearly see that this is a symmetric shape. This is symmetric about the line y equals b. So therefore, the y bar of this is already taken care of for us. The y bar is simply b. It's a symmetric shape about this line here. It's just y equals b. So the y bar is equal to b. So we only need to concern ourselves with the x bar. Yay. Okay. So then let's do that thing I said. Let's see. So the dA then, let's draw out the dA. Let's draw the dA. Well, this is going to be dx times, okay, the height of this is the difference between the two curves. So this is going to be 2b minus b over a squared x squared, that's the top curve, minus the bottom curve, which is b over a squared x squared. And this just comes to simply 2b minus 2b over a squared x squared. So that'll make the integration a little bit simpler, actually. So I can use the same dA to find the area. Let me just do that really quick. Area is simply going to be the integral of dA, which is going to be the integral of 2b minus 2b over a squared dx, which I can just pull out the 2b if I'd like here. So that's going to be the integral of, from 0 to a, thank you. From 0 to a, which is going to be 2b 0, I don't have the x on here because I'm just taking I'm getting the area, just the area. 1 minus 2b over a squared, or sorry, just 1 over, you know what, I don't think there's actually a lot of benefit to splitting this up. Integral of 2b, which is simply, you know what, yeah, this is just simply, all this is a constant times x. So 2b minus 2b over a squared x evaluated from 0 to a, which is then, let's see, 2b minus 2b over a squared times a, which is 2ba minus, sorry, 2ba over 2b over a. Yes?
How, this is a side note, on your tests, how strict are you about skipping algebraic steps in integration?
Okay. Depends. Then, so 2b over this, or let's see, if I really wanted to be a pain in the butt about this, I could, no, I'll leave it alone. Actually, I'm probably going to end up with something like this anyway, so I'll just go 2b a squared minus 2b over a. A is equal to that. Oh, my minus sign went away. 2b a squared minus 2b over a. Yes?
Whenever you did the integration, you had, so at the top you had negative 2b over a squared times x squared. I think you forgot to bring that down.
Oh my goodness, did I really screw that whole thing up? Wow, I'm so sorry. I'm spacing out today. Can you tell it's almost the end of the semester? Sorry about that. I was wondering why that was such an easy integral. Helps if you write the right integral. So thank you, derp. 2b minus 2b over a squared, sorry about that, x squared dx. Now I will pull out the 2b, because now it actually does make sense to do that. 2b integral 1 minus x squared over a dx, right? Over a squared. Yes. So then that will be 2b times x minus x to the third over 3a, a squared, yes, evaluated from 0 to a. To a. So that will be 2b times a minus a to the third over 3a, a squared. So that's 2b times, this is basically a over 3, so 2a over 3, which then reduces to 4ab over 3. and that's the overall area of this thing. That's the overall area. That's the overall area of this thing, and we're going to need another slide for this. Assuming I didn't screw anything else up, which is certainly a possibility. Okay, you got this?
How did you test? Explain to me how you tested for the symmetry again.
How did this explain how I tested for the symmetry? How I knew it was symmetrical, or how I knew it was symmetric? Well, I knew based on the slope of the parabola, based on the x squared term. Okay, so we have that. Now, so we have our A. Now we need to get the, so first I'm going to do some transposition. So I know again that A is 4AB over 3, right? 4AB over 3. And our dA for this, for our integration, is 2b minus 2b over a squared times x. 2a minus, and of course there should be a dx in here too, but that's okay. Minus 2b over a squared. 2b over a squared x squared. Yeah, 2b minus 2b over a squared x squared dx. This is just from this right here. Okay. Then let us say that I know again that the qy is going to be equal to x dA, the integral of x dA, which is going to be, in this case, equal to the integral of, wait, something, oh, sorry, that was 2b here. Helps if you,
Okay, that's. Where is this coming from?
dA equals 2b minus b squared over a squared, right? No, b squared minus, sorry, 2b over a squared. Keeps erasing things. Let me just do the presentation. It keeps erasing things. Or not it keeps converting them to images. Sorry. Just a second here. This is giving me problems. Okay, so just as a reminder, dA equals 2b minus 2b over a squared. x squared. There we go. Now I have it. And then qy is going to be the integral of x dA. And there probably should be a dx here as well. But this is going to be x times, so the integral from 0 to a of x times 2b minus 2b over a squared x squared, oh, not like that, x squared inside the parentheses, x squared dx, or the integral of 2bx minus 2b x to the third over a squared dx, or 2b times the integral of x minus x cubed over a squared dx, or 2b that, so 2b times x squared over 2 minus x to the fourth over 4a squared, evaluated from 0 to a. So then this is 2b times a squared over 2 minus a to the fourth over 4a squared. That goes away and becomes squared. Okay, so this is 2b minus a squared, or times a squared over 2 minus a squared over 4, which is 2b times a squared over 4. And finally, qy in this case will be 2a squared b over 4, or a squared b over 2. That's qy. And then finally, x bar is equal to qy over a, which is then a squared b over 2 over 4ab over 3, which is a squared b over 2 times 3 over 4ab. Boom, 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 boom. So I get 3a over 8. So the centroid, assuming we didn't make any other math errors, which is a certain possibility, assuming we didn't screw the math up, would be 3a over 8, comma, I'll come back to this, don't worry, b. Like so. And that's it. Simple. What could be easier? Just like drinking water. It's so simple. It's the simplest thing in the world, right?
You can integrate faster in your mind than I can write.
Well, I kept making errors, so there you go. I think that's it. There may be some math error in there somewhere, but that should be it. Something that's the right process anyway. Barring any calculus errors, that should be the correct solution.
Is this representative of what might be on the test?
Okay. All right, we'll sit here for a bit while people feverishly copied around my chicken scratch. So what do you think? Centroids via integration. Centroids via integration. Conceptually, it's not that bad. It's just setting up the integrals and doing the integrals that's the problem, really.
At least they're easy enough to work with.
Of course, if I really wanted to be evil, I could give you a shape that'd be like, I could ask this on an exam, like, give you a shape that would be like, imagine like if You know, if you really wanted a challenge, you could do something like, okay, maybe it's a polar integral and like the shape, the center line of it is like an Archimedean spiral. And then the width of it is non-constant, like the width of this thing is varying as like a sinusoidal function or something.
Give me all the time in the world, I wouldn't be able to figure it out.
Maybe there's a natural maybe there's a natural logarithm in there somewhere. You know, we could have integrals that's a combination of sines and cosines and natural logarithms. It'd be wonderful. No? Okay. Oh, okay. Let's see. And this is just another composite area problem. A thin homogeneous wire is bent to form the perimeter of the figure indicated. I think this one is fairly straightforward. I don't know if I need to even work through this one. Do you think you can figure out this one? Actually, you know what? I will show you. I will show you this one. Okay, yes.
Oh, just by looking at that, can we tell that that's a circle, a quarter circle?
Yes, we can tell it's a quarter circle just by looking at it because it has a radius indicated.
Well, that's a good sign.
Okay. So what is this made of? This is made of this is another composite area one. And it's made of two pieces. So thankfully, we're not going to need to do I'm not going to do the integration on this one. It's made of a quarter circle with positive area, and it's made of a square with negative area. So here, area is going to be, well, pi r squared over 4. So pi times 10 squared over 4, so 25 pi inches squared. 25 pi inches squared. The area, is going to be simply base times height, or it's a square. So just 5 times 5 equals 25 inches squared. However, I'm going to say this thing has a negative area. This is a hole. This is a hole in the shape. So I'm going to do the same calculation I've done before, except with a negative area. The x bar here, if we look on our, well, we can see that circles and quarter circles have centroids. 4r over 3 pi is 4r over 3 pi is the formula from the book. 4r over 3 pi. So 4 times 10 over 3 pi. So 40 over 3 pi. That is the measured from the corner. That is how you find the centroid of a quarter circle. And y bar is the same for a quarter circle. It's 40 over 3 pi as well. Here, the x bar is going to be, the x bar and y bar will just be at the center of the square. So 2.5 inches. Note, we do not use a negative coordinate for the centroid. We only apply it to the area. The coordinates are still just the coordinates. So then the overall x bar, so these are our pieces. In fact, maybe I'll put like I here, I here, I here.
Is that like a big X bar, really?
Yeah, this is like a really, if I really wanted to do it, I could put like a capital X bar or something there if I really wanted to. It's just the overall X bar. Overall X bar is going to be, all right. So I see 25 pi times 40 over 3 pi plus negative 25 times 2.5 over negative 25 plus 40 over 3 pi. Oh, derp. No, that's not right. Sorry. Plus 25 pi. Yeah. And that's just going to come to an ugly decimal, so I'm just going to throw that in the calculator. If I wanted to make my math teacher happy, I could go and actually solve that in terms of pi, but it's summer, so I don't care. 40 over 3 minus 25 times 2.5, and then divided by negative 25 plus 25 pi. And I'm getting 5.05, actually 5.06 inches for the x bar. 5.06, yeah. 25 pi times 25 times 40 over 3 minus 25 times 2.5. All that over negative 25 plus 25, yeah. And, you know, the y bar should be the same, shouldn't it? And y bar, it's symmetrical about the line y equals x. It should be the same. Y bar should also be equal to 5.06 inches.
Just by visual inspection, you're pretty close to where the B dot is there.
Precisely, yes. So I can say now, I can summarize, x bar, comma, y bar, and for those who are maybe questioning, the reason that the x bar and the y bar, I can simply say that they're the same, is that for each piece, its x bar and y bar are at the same coordinates. So you notice the x bar and y bar coordinates of this piece are the same, and the x bar, y bar coordinates of this one are the same. 5.06 inches, comma, 5.06 inches. Like so. And that is it. All right, questions on what we've gone over today? No, you don't have to memorize the formulas. I'll give you that during the exam. Okay. But you will need to be able to do simple things by integration. So, you know, that what I'm going to ask you to integrate will be a fairly simple one, like a polynomial or something like that. We'll see. The hardest you might have to do is integration by parts. We'll see, though. No. Okay. Anyway, that'll do it. Okay, so again, tomorrow we have the penultimate lecture for the class on, that's a great word, penultimate. Then on Tuesday we have our final lecture, and then we have the final after that. So, I'll see you all tomorrow. Be ready for a class again tomorrow. We'll go over some of these practice problems if you can. Tomorrow we'll be working on moments of inertia. If you need assistance, I'll be in my office after this. I'll see you tomorrow, and as always, thank you.